everyone, welcome to the channel. In today's video, we'll explore the theoretical aspects of SonarQube and understand how this powerful tool automatically measures the quality of our code. We'll focus on what SonarQube is and discuss its key axes of quality evaluation. In an upcoming video, we'll have a practical demonstration where we'll install SonarQube locally using Docker and perform a real-time analysis. So let's dive in and discover how we can elevate our software. Before talking about SonarQube, let's think about common problem in software development. How do we know if our code is good? In the past, the only answer was, well, it compiles, or the users aren't complaining. However, as projects become large and more critical, code quality has become essential for avoiding errors, vulnerabilities, and maintaining issues. This is why we need tools to automatically measure code quality. This is exactly where SonarQube comes in. SonarQube is a static analysis platform that evaluates software quality without running the code. It identifies issues such as bugs, bad practice, duplication, and poor documentation through specific metrics that reflect the overall health of the code. SonarQube is available in various editions to suit different needs. For example, the Community Edition, that is an open source edition providing core functionalities to analyze multiple languages through free plugins, and is ideal for small teams, open source projects, or tools starting with quality analysis without extra cost. Other example is commercial editions such as developer or enterprise. Advanced features include multiple branch analysis, pull request reviews, additional quality rules, advanced dashboard, and official support. Is ideal, for example, for large organization requires scalability and deep integration within development process. Other example is SonarCloud. Is basically a cloud-based solution for Sonar Source that lets you analyze code without need to manage your own local server of SonarQube. Is, for example, a native integration with CI/CD platform like GitHub Actions, Bitbucket Pipelines, and Azure DevOps, and have a free for open source project with competitive subscription available for private projects. Is ideal for teams preferring cloud managed solution without infrastructure overhead. Now, we'll deep dive into the 7 fundamental axes SonarQube used to evaluate code quality. These axes cover essential aspects that affecting our software's overall health, from detecting errors and vulnerabilities before production to ensuring our code remains understandable, maintainable, and scalable over time. Understanding these 7 areas thoroughly allows us to identify key improvement points in our software and avoid future technical problems. So let's review each one in detail. The bugs are errors in the code that can lead to runtime filters, impacting system stability and reliability. So, why is this important? The bugs in production can cause critical errors, data loss, or application filters. Detecting bugs early improves software stability and avoid costly correction later on. SonarQube helps, for example, detecting common bugs like null variable access, incorrect loop use, logical error, etc. So Sonar classifies issues by severity. The severity, for example, is blocker, critical, major, minor, and info, and provides clear visualization on dashboard, helping prioritize bug fixes. Here is example. This code will cause a runtime exception because it attempts to access the length of a null. So, coding rules are best practices that help keep the code cleaner, more structured, and easier to read. So, why is this important? Well, writing code is easier to maintain and understand, reduces likelihood of future errors and problems, enhances developer collaboration. So SonarQube helps, for example, applies standards such as Java code conventions, suggests improvements in code structure, and helps prevent spaghetti codes and risky coding practices. For example, a bad practice, it's unnecessary to compare Boolean directly with true simplifies your condition. The next important point is the test. The test coverage measures what percent of code is covered by unit or integration test. So the test is very important because code without test is more prone to errors, and good coverage helps to detect problem before reaching production and provides confidence when making code changes. So Sonar helps, for example, show the test coverage percent, identifies unit test part of the code, and suggests increased coverage for critical function. For example, here we method to check if a number is even or odd, and we've added this to validate its behavior. The following is code duplication. Code duplication occurs when identical code fragments are repeated in several places, increasing complexity and risk of errors. So, code duplication is important because if an error is found, it must be corrected in every duplicate instance. Increased maintaining effort can lead to code inconsistency. So SonarQube helps, for example, identifies duplicate code fragments, provides suggestion for reducing duplication, and encourage code reuse. Here's an example. These two code blocks perform the exact same function, so this is unnecessary increasing maintainer effort. So SonarQube assesses whether code is properly documented, especially APIs and public functions. So the comments is important because makes the code easier to understand for other developers, accelerate the maintenance and debugging process, and improves the team collaboration. So SonarQube helps to detect undocumented function, evaluates documentation quality, and provides suggestions to clarify code documentation. Here's an example. Here is a clearly documented method that calculates the area of a circle given its radius. The next is architecture and design definition. SonarQube evaluates if the code follows a well-designed architecture, free from circular dependencies or, for example, solid principle violations. The architecture is important because a clean design makes the code scalable and maintainable, and, for example, prevent problems like circular dependencies and poor modularity. So Sonar, for example, detects solid principle violation, identifies model dependency issues, and highlights areas and high coupling. Here's an example. This show circular dependency, complicating project scalability and maintainability. So the last one is complexity definition. The cyclomatic complexity measures how complicated a method is based on control flow structures. For example, if, for, or while, etc. Is this important because code complex is difficult to understand and maintaining, and prone to more errors and unexpected filters. So SonarQube helps to measure the cyclomatic complexity of each function and suggests, for example, reduce decision structure such as if, which, etc. And in this example, this method contains excessive nesting, creating unnecessary complexity and reducing readability. So let's focus on SonarQube architecture. We'll be using the diagram shown on the screen and details from official documentation as our guide. In the diagram, we see three main sections. One is the scanner CI/CD, which scans the code. Two is the SonarQube server, composed of several internal processes, for example, web server, compute engine, and search server. And three is the database, where result and configuration are stored. So let's break down each component. So first is the scanner. What is it? The scanner is the tool that integrates with or build our CI/CD process. It analyzes the source code files in search of potential issues. How does it work? The scanner, along with language analyzers, for example, Java, JavaScript, Python, etc., reviews the code for issues, bugs, vulnerabilities, and more. Um, Once the analysis is complete, it generates a report containing information about code quality. This analysis report is sent via HTTP or HTTPS to the SonarQube server. This communication is essential to that the server can process the result and present the findings to development team. The second is the SonarQube server. At the core of the architecture is the SonarQube server, which has three main processes working in coordination. First is web server, handles the SonarQube UI through this web interface. Users view analysis results, configure projects, quality profiles, manage users, and more. So any action you do via a browser, such as viewing book reports, first go through this web server. Two is compute engine. The compute engine acts as the brain that processes the analyzed reports sent by the scanner. So when reports arrive, the compute engine takes the data, validates it, applies SonarQube logic, such as quality gate, thresholds, etc., and writes the result to the database. So incoming process are queued, ensuring orderly and efficient process without overwhelming the system. So the 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 last one component is search server. This is powered by Elasticsearch that facilitates fast search and filtering of analysis data. And the function is that indexes the scan results so that search and filtering for specific issues or metrics is quick and efficient So the other key component is the database. So the database store all analysis results such as metrics, issues, project history, and SonarQube configuration, for example, quality profiles, user account, access tokens, and more. Ideally, the database should be on a different host than the SonarQube server to improve performance and avoid resource conflict. So SonarQube supports various external databases such as PostgreSQL, SQL Server, Oracle. So it's crucial to follow a specific configuration for each one. Let's see how information flows within the entire architecture. One is code development. In the CI/CD environment, the scanner is triggered to analyze code. Two is report generation. The scanner inspects the code, creates a report, and sends it via HTTP or HTTPS. Three is reception in SonarQube. The report arrives at the web server and is placed in a queue for the compute engine to process. Four is processing and storage. The compute engine analyzes the report, applies quality rules, and saves all results in the database. Five is indexing and search. The search server, in this case is Elasticsearch, indexes the data so that the web server can quickly deliver dashboards and reports. So six is result review. The users connect to the web server to view metrics, trends, and any detect issues aided by Elasticsearch indexed. So the best practice is that separate the SonarQube server and the database to reduce load on a single machine and improves scalability. Other best practice is synchronized time. All hosts should have their clocks synchronized to avoid inconsistencies in analysis logs, and configure volumes and storage in Docker environments. For example, store data and logs on external volumes for simpler updates and recoveries. So that's the core of SonarQube architecture. We cover the scanner, which prepare and send the analysis, the SonarQube server with its three main components: web server, compute engine, and search server, and the database, which store all the results and configuration. Each part plays a crucial role in continuously monitoring code quality and help teams take action. So, if you found this video useful, don't forget to hit like and subscribe for more content on software development tool and code quality. See you next time and thank you.